we would like to go to the second speaker, Mr. T. Wakayama from INPEX. Mr. Wakayama, are you ready? So we have the next presentation on research and development in CO2 utilization technology. So I request Mr. Wakayama to make his presentations, please.
Yes. Firstly, I'm sharing the screen. Can you watch the screen?
Yeah, that screen is there.
Visible. Screen is visible.
You can make it in the presentation mode.
Yes. So, can you watch my presentation?
Yes, your presentation is visible. Just make it in the slide mode.
Yeah, good. So, good afternoon, everyone, again. So, I'm Tatsuya from INPEX. I'm very pleased and honored to be here today. So, I'm belonging to the new business planning group, also the new business planning unit in the renewable energy and the power business division in INPEX. So today, I would like to introduce an Nagaoka CCU project for the effective recycling of CO2 to produce methane. This project is supported by NEDO and METI, the government. So before methanation, so I'd like to...
Mr. Wakayama, just a minute.
Yes.
Please make your presentation in the slide mode.
Slide mode? Before this presentation, I checked
So can you make it full screen, sir?
So you can suggest to the
full screen, sir. Full screen.
Full screen, yes. Is it better?
Yes, sir. Perfect, sir. Perfect.
Yeah, good. So INPEX Corporation is Japan's largest exploration and production company and a mid-tier E&P player, just behind the world oil majors. So INPEX involved approximately 70 projects across more than 20 countries. So we have two large LNG projects in Australia and Indonesia. So Australian one is already started. It's exported to LNG to Japan and overseas. The other one is still under feed. So both of our projects, it's each at 9 million tons of LNG per annually. Also, the INPEX is one of the special class share held by the Minister of the Economy, Trade and Industry. It's a NEDO. So in May 2018, INPEX announced the Vision 2040, setting 3 key business targets. In its quest to become the leading energy company, meeting the energy needs of Japan and the country around the world. The first one is the sustainable goals of the oil and natural gas E&P activities. So final goal is top 10 in the world. Second one is the development of the global gas value chain business, the targeted players. The final one is renewable. The enforcement of the renewable energy initiative is 10% of the portfolio, our portfolio. So these the targets of phase to the reduced carbon footprint. So through the reduced carbon footprint, that finally leads to the continuously and sustainably increased corporate value. So we already started the project for the renewable energy, such as geothermal power, PV and wind turbine power generation project in Japan and overseas. So one of the breakdown of the Vision 2040 is construction of the value chain with electricity, the hydrogen, and the methane as secondary energy. As you know, the value chain of the electricity and the methane is already in place widely in Japan. The hydrogen, the electricity and the hydrogen do not generate CO2 when used. The hydrogen and the methane are easy to storage, so, but the hydrogen is liquid hydrogen is so low temperature, half. So by the producing the methane as a secondary energy through the methanation, so we will create the value chain that can utilize the existing energy infrastructure. It's a key point. So this is our conceptual illustration of our CCU project. So INPEX is also engaged in the carbon recycling project that involves the process known as the methane synthetic natural gas or the CO2 methanation. So from the start from the renewable power, it's like solar and wind power. It's an input. So this technology produces electricity for the electrolyzer. So electrolyzer they produce that renewable hydrogen. Then other one, so CO2, we have a lot of the CO2 sources. So we gathering the CO2 and the hydrogen into the methanation process. So after the methanation, so we got the synthesis to natural gas by renewable energy. So put in our existing pipeline or our energy infrastructure to transfer to the consumer. So finally, so the synthetic methane is sustainable for the fossil natural gas. Use of the CO2 and expanding the introduction of the hydrogen and delivered from the renewable energy. It's our concept. So, methanation consists of two chemical reactions when hydrogen is produced by electrolyzer. So the first one is a water splitting to produce hydrogen. So it's the easy reaction. So 4 mole of the CO2, H2O, to produce 4 mole of the H2 and 2 mole of the oxygen. It's required the 4.5 kilowatt hour or more per normal cubic meter of the hydrogen. So it's we selected the 10 type of the water electrolyzer. So that's produced in Japan, such as Zosan, Cobalco, and Honda, and Toshiba, and so on. Second reaction is methanation. So 1 mole of the CO2 plus 4 mole of the hydrogen and convert to the 1 mole of the methane to plus 2 mole of the hydrogen and heat energy. So the system is a reaction in place reactor packing in nickel and catalyst. It's like a steam opposite side of the steam reforming of the methane. So catalyst supplier in Japan, so it's Zosen, Qatar, it's to the group, and IHI, the Children, agent and so on the university side as well. So this equation suggesting four mole of hydrogen, one mole of the hydrogen lost in two mole of the hydrogen in the methane. So we have to consume, utilize the heat power. It's the key point. So this is the roadmap of the commercialized methanation technology for future from now. So it's the trend we hear now. The y-axis is the amount of the CO2 utilization. It's a unit, what's the unit? Amount of the per unit. So finally, we will construct in the large scale of the methanation process. It's about 16 kilo normal cubic meter CO2 per hour. It's a commercial phase. Its equivalent is 100 million, 1 million ton of the CO2 per year. So, but we are here now. It's still it's a small. It's a 8 cubic meter CO2 of the per hour. It's a fundamental technology development phase. So, fundamental technology development phase and the commercial phase is so quite different. It's a lot of the distance. So, therefore, we have to stepwise the R&D through the technology development phase and the demonstrating phase. So by the stepwise step R&D, so we will success with the large scale of the methanation process or cost down. So at the 2030X, over 2030X in the commercial. So this is the organization chart of the project. INPEX and Hitachi Zosen plays as a direct contractor with NEDO. So this project period from the fiscal year 2017 to 2020. So of course, there's also the budget from the MED. So we have the academic side. First one is under our umbrella, National Institute of Advanced Industrial Science and Technology, AIST, you know. So other one is under the Hitachi Zosen umbrella. So now university. It's contracting and cooperating each other closely. So in recently, so the CSRO in Australia joined our project for the pre-feasibility study in Australia for the methanation. So it's so basic the chart. So this chart shows the four our research objectives. The first one is a scale up the reactor and the system. So it's it's operated from the INPEX our company and those. So first we started with 0.1 normal cubic meter per hour. So we already constructing the 8 cubic CO2 per hour. So finally, so we scale up and scale up. So we the 400 normal cubic meter CO2 per hour. So it's a target. So only the bulk research and R&D system. So two academic sites supported about the research and technology. So first, second is the mechanism. Third one, the simulation. So second and third and the macro R&D objectives, AIST and the Naga University clarifying the reaction mechanism and simulating the reaction mechanism. course. So mainly, we combine.
Excuse me, Mr. Wakema, can you speak a bit louder, please? A bit
Yes.
louder, please.
Is it okay?
Okay.
Okay. So first, as a macro R&D objectives, INPEX are conducting a comprehensive techno-economic analysis of the methanation system. So in the reaction heat energy management technology and development, the simulation inside the reactor is carried out. This is an example of the shell and tube type of the reactor for the single tube of the cylinder type, shell and tube. But for the white, so you can see the white the circle obtained in actual experience. We conducted a simulation based on the experimental condition and the physical property values. So accurate and fitting has been made for the both and catalyst temperature and product gas temperature. And the catalyst temperature distribution in the reaction, the vessel is reproduced. It is so nice simulation that we got. So in addition, the result obtained the single tube, the cylinder tube will apply to the multi-tube cylinder tube type of reactor. Also, lab scale of the plate reactors become to the actual size plate type reactor, and numerical calculations were performed to resolve all region of the gas, solids, and liquids we are processing now. So last October, INPEX has begun the methanation test at these facilities. So it's an overview of our natural gas plant. So called the Hoshijihara plant at the Nagaoka City in Niigata Prefecture. It's far from the JR station, Nagaoka Station. It's 30 minutes by taxi and car. So we have the three trains, the natural gas treating system. First one, the second one is around here, and the third one is here. So this plant is a yellow indicated yellow dot. The CO2 from our natural gas plant to the test plant. So all utilities needed to operate the test plant supplied from our natural gas plant. So especially as for the CO2 for the methanation, so the reservoir CO2 from the gas well induced through the amine unit through the blue pipe line, line to the test plant. Also that electricity and water, the potable water, the compressed air, the waste water from the test plant, we treatment in our test plant. So you can see this is our test facilities. So wide is 20 meter, depth of the 10 meter, and height 10 meter high. It's so big. So because a lot of regulation in gas field, so we have distance of the fire or leakage that the layout is so wide. So our supply to the high voltage energy, this high voltage receiving panel here, and then this panel supplies high voltage electricity to the PEM type of reactor. This type of the electrolyzer produces the hydrogen and oxygen through to the container. Finally, so hydrogen and CO2 put in this type of the reactor. Those electricity can be produced methane, almost 100%. to the other container one. So this is the system for of the test plant. So already I mentioned. So electricity from our GTCC plant, the provided electricity to the PEM type of reactor, electrolyzer. So this can be produced as a hydrogen as a 5 nines through input through into the container 2. On the other hand, CO2, our reservoir CO2, firstly put in the dehydration of the reservoir CO2. So we go to the crude CO2 to the electrolyzer for the removal of H2S from the crude CO2. So purified CO2 put in the container 2 and the mixing hydrogen and CO2 for the suitable ratio and pressurized in 0.8 megapascal gauge for the reaction. So finally, so we send the mixed gas to the pressurized methanation reactor here, and then reaction, the methanation reaction does occur. Return back to the crude methane to the container 2. In the container 2, so we have the membrane type of the purificating system. So it's upgrade to the crude hydrogen to the purified methane. But unfortunately, so it's a so small plant and it's a test plant. The purified methane, so we have to treat the gas flare with the burning. So we shifted from the manual operation to automatic operation with the fail system. So finally, so we become the long-term operation. So it's one of the results. So this is the flow rate of the hydrogen and CO2, Y2X axis. The X-axis is the operation time. So it's a full load. The 8 cubic meter of the CO2 and 32 normal cubic meter hydrogen per hour combined in the reactor and the reaction. Finally, we got the methane. It's a concentration of the methane. So this is our target concentration of the methane after our purification system. So this result indicates that it's so close to our target. So sometimes we pass our target. So after the so we confirm that our the reaction properties. So after the various test operation in which temperature, the pressure, and operation load, etc., and changed, it is planned to be shifted to the full continuous operation before winter in Japan. So this is the final slide. So it's a summary. So CO2 methanation technology can reduce the CO2 while using the existing natural gas infrastructure. It's so key point. So the hydrogen is one of the special energy for the future, but nobody has a hydrogen infrastructure. So it's if we construct the hydrogen infrastructure value chain, so to reduce the construction, so it's a lot of the money and a lot of the time, the efforts. So next one is a commercial scale plant of the 60 kilo normal cubic meter per hour as an over 2030 1 million tons of the CO2 annually. So if we the lot of the CO2 more, so we will introduce a lot of the train of the methanation system. Third one is the economics. The methanation mainly depend on the electricity or hydrogen price of the renewable energy. So it's one of the key point. So the hydrogen is still hydrogen price is still high. So Japanese government also we have the target price in hydrogen in the future, but it's still high. So if the hydrogen the 20 Japanese yen per normal cubic meter, so we produce if we produce a methane, it's simply estimated 80 Japanese yen per normal cubic meter of the methane. So we have to reduce the cost of the hydrogen for the larger scale or something. So finally, under certain conditions, the electricity price is below the 3 Japanese yen per kilowatt. The IRR is roughly estimated to be 9.5%. It's let's say our target. So of course the estimated condition is a so frequency. So if we have to methane and hydrogen from an electrolyzer and heat power for the other plant, so it's IRR is still little bit increased maybe. So that's all. Thank you for attention.
Thank you, Dr. Wakayama, for giving an insight on this very important project of CO2 utilization. I'm sure this methanation-based CO2 utilization technology is going to be one of the key technology for the world's decarbonization efforts. May I now request Dr. Fumihiko Yoshiba. Dr. Fumihiko Yoshiba from Central Research Institute of Electric Power Industry, Japan, to make his presentation on contribution of coal-fired power plants flexibility to a power system. Mr. Yoshiba, please.
Thank you very much. And can you hear me and can you see the slide?
Yes, we can do
We can
that.
very much hear you, and the slide is visible. Only thing is to put in the presentation mode or full screen mode.
Okay. So thank you very much for the opportunity for me to present my research results. And I will...
Mr. Yoshiba, please share your screen. Do not share the application.
Not the application. Share.
いいんでシェアしてってことです。パワポを共有するんじゃなくて、画面共有。
画面共有ですね。
はい。
シェアマイスクリーンか。そっか、こっちか。ありがとうございます。あれこれいいのかな？
It's good now. It's good now.
Okay. Thank you. And thank you very much for the opportunity for me to present my research results. My name is Yoshiba. I'm working in Central Research Institute of Electric Power Industry. My presentation title is Contribution of Coal-Fired Power Plant Flexibility to a Power System.はい、行きました。ありがとうございます。Okay, in this slide, in this figure, the power and demand in southern island of Japan on May 3rd, 2018 is described. May 3rd is a national holiday in Japan, and the electricity demand is very low. During the photovoltaic power increase in daytime, pumped hydropower pumps up by using the electricity, and the thermal power plants are operated under the minimum load. Here. Because the installation of photovoltaic power is accelerated these days, thermal power plants need to have more flexibility for the stable demand supply balance control. This is the background of this study. The thermal power plants need flexibility for stable demand supply balance of the demand supply balance and flexibility. Frequency of the system during the introduction of intermittent renewable energy. Contribution of this flexibility on power system needs to be identified in the market. So the purpose of this study is to develop a methodology to evaluate a contribution of thermal power plants flexibility to the stable power supply. First part of this presentation is about the classification of LFC performance of power units. In order to evaluate the contribution of flexibility of thermal power plants, a classification of load frequency control performance, or LFC performance, is introduced. In this slide, LFC performance classification is explained. For example, GTCC ramps up like this line from output power, delta megawatt is 0 to several 10 megawatt here. And for the coal power plant here, this is ramps up like this way, but they need another time on the response delay of like around 6 minutes here. And load frequency control, LFC performance, is classified with respect to AOR, or available output range here, and max FAT, or maximum full activation time in this right-hand side figure. So performance of GTCC locates here, and coal-fired power unit locates here. So the unit having larger AOR and shorter max FAT has high performance. So these units are classified as very high performance, followed by high performance, medium performance here, and low performance here, respectively. So this is the classification of the LFC performance, load frequency control performance. AOR and max FAT is defined in the equation in this table, and AOR is expressed using this equation, and max FAT is the equation as this. This is the delay of the response, and this is the AOR divided by ramping rate. In this table, power mix of AGC30 model is listed. AGC30 is applied in this calculation. AGC30 is automatic power generation model defined by Institute of Electrical Engineers of Japan. Power grid capacity is medium size in Japan, and the capacity ratio of power units corresponds to Japan's average capacity ratio. This ratio is average ratio of Japan. So this is nuclear, and this is all the thermal power plant, power unit from oil, LNG steam. This is a liquefied natural gas with the steam cycle and the GTCC and coal-fired power plant here. Run-of river is base load here, and pumped hydro works with this. And for the fuel price in Japan, most expensive one is oil, followed by natural gas. Natural gas is both used in LNG steam cycle and GTCC, and coal is the cheapest fuel in Japan. And because Japan is a resource-hungry country, and all of the resources are imported from overseas, and natural gas is liquefied and imported to Japan. So, calculated cases in this study are listed in this table. In case 1, a simple merit order is applied in the selecting procedure of the LFC unit, whereas the LFC performance is classified in case 2 and 3. For the LFC performance of coal-fired power unit, base performance is supposed in case 1 and 2, and the advanced performance is applied in case 3. This advanced performance of coal-fired power unit is described later. Power demand and residual load is described in these figures. Power demand curve is this top of this line, and PV generates this area, and PV capacity is changed from 3.3 gigawatt to 26.4 gigawatt in this analysis. So residual load that the thermal power plant and pumped hydro must cover is from 0 to this value, this height. This is the residual load. So the power unit commitment discussed later is calculated every 30 minutes, and frequency of the system is calculated every second. Here. The daily unit commitment of case 1 and case 2 is described in upper part of this slide. And LFC, load frequency control reserve, is drawn in the lower figure. Here, and here, this and this. Here, the pumped hydro pumps up in daytime and generates electricity in the night time. The base load is nuclear and run-of river, and many of GTCCs and LNG steam, natural gas steam unit, stops operation in daytime, except the LFC control reserve. Since the LFC unit is selected by simple merit order in case 1, the coal-fired power unit is mainly selected as LFC reserve in case 1. In case 2, LFC unit is classified. Thus, the GTCC and LNG steam unit covers the LFC reserve in this case. So, the daily unit comment, this is a frequency. In this figure, the frequency deviation is compared for case 1 and 2. Since the coal-fired power unit is selected as LFC reserve in case 1 by merit or only by a merit order, the frequency deviation exceeds limit of 0.2 Hz. Here here and here and here. This is case 1. The frequency deviation in case 2, on the other hand, is managed in the range of 0.2 Hz to minus 0.2 Hz. This line is the case for the case 2. So the frequency deviation is managed within these regulated range. By the result of these calculations, it can be said that the classification of LFC performance helps the way to stabilize the demand and supply balance or frequency of the power system. The second part of this presentation is on the effect of an improvement of coal-fired power units flexibility on fuel cost and CO2 emission. For the purpose to estimate the improvement of flexibility of coal-fired power unit, 2 cases are supposed. In base case or in case 2, normal performance of coal-fired power unit is defined. There is an operation mode change at the load ratio of 60%, and 5 mills are operated in upper load, and where 3 mills are operated in lower load. In advanced case, or in case 3, operation mode changes at the load ratio of 40%, and 2 mills are operated in the following lower load range. So the flexibility performance of the base and advanced coal-fired power units are compared in this table. The minimum load, the minimum output rate is improved from 30% to 15% in advanced case, and the ramping rate is improved from 2% to 3% in upper load band, and from 1% to 2% in lower band. The technology applied in the advanced coal-fired power units are wide-range operational burner and rotational speed controllable mills and rapid move of throttling valve of high-pressure steam turbine. By the improvement of flexibility of coal-fired power units, the classification of LFC is changed from N, this is a formal base case, and this is advanced case. So the classification is changed from N to non-available to high performance in case 3, which can be applied to the LFC reserve operations. The results of calculation of unit comment is described in this slide. In PV capacity this is all the cases, case 3. This is, in this case, flexibility of coal-fired power unit is improved. In PV capacity is 13.2 gigawatt case. The LFC reserve is mainly covered by coal-fired power units in daytime. In nighttime here, since coal-fired power unit works as a base load, just the GTCC and LNG steam unit are employed as LFC reserve here. In PV capacity is 26.4 gigawatt case, there is a suppression of PV output here, and coal-fired power unit operates at very low load at daytime here. Because the LFC performance of coal-fired power unit at low load is very low, GTCC needs to help the lack of LFC reserve here at the daytime. So GTCC covers the LFC performance of coal power in daytime. In these figures, the fuel cost of all the thermal power units are compared for case 2 and 3 with the parameter of installed PV capacity here. Since the coal power unit covers LFC reserve in case 3, the fuel cost of all the thermal power unit is lower than case 2 for all of the PV installed capacity cases. For CO2 emission in case 3 is bit lower than in case 2 here because the LFC is covered by coal-fired power plant power unit in case 3. The LNG steam unit is no longer used as LFC reserve. So the LFC steam unit stops their operation in case 3. Consequently, total amount of the thermal power units generating in the power grid is smaller in case 3. And more renewable energy is introduced compared to the case 2. This is why the CO2 emission in case 3 is lower than in case 2. So let's skip this slide and okay. This is a slide and I do not read this, and that's all of my presentation. And thank you very much for your attention. Thank you very much.
Thank you, Dr. Yoshiba, for making an excellent presentation on coal-fired power plants' flexibility to a power system. You talked about load frequency control. You also talked about performance available output range. And I'm sure there will be several questions which we will take at the end of the session. Now I invite Mr. Kamachi Razwell, Corporate Advisor, Mitsubishi Hitachi Power System Limited, to make his presentation on environment management for thermal power plants. Mr. Kamachi Razwell, please.
Mr. Rajwal, we cannot hear you, sir. No, sir, we cannot hear you still. Mr. Rajwal, sir, are you using a headphone or something, sir? Mr. Rajwal, can you try with the headphone? Sir, can you check your audio connection, sir? We are unable to hear you.
Mr. Rajwell, would you re-log in, I think? Would you re-log in and try again?
Subodh sir, I'm on call getting my check.
Okay. In the meantime, I may request all the delegates to put their questions in the chat box so that at the end of the session, those questions can be taken up with the respective presenters.
I think there is a technical glitch, Subodh sir. We are unable to listen to him. Hello.
Okay. So What do you suggest? We should take up the questions, please.
Yeah, we can take the questions. Yeah.
So, do we have some questions in the chat box? We open this session for the question answers. So please put the questions in the chat box.
Very good afternoon, sir. We have got the first question. What intervention retrofitting is being done to safeguard against not much fall in efficiency when we are cycling our units and for sustained low load operations? So this is the first question being asked.
This question is for Dr. Yoshiba, please, I think.
Yes, yes.
Dr. Yoshiba,
Shall I repeat the question?
I think you should.
Dr. Ishwar, what intervention or retrofitting is being done to safeguard against not much fall in efficiency when we are cycling our units and for sustained low load operations?
Excuse me, can you tell it more specific?
I think the essence of the question is how to optimize the efficiency when we are aware that the plant will be running at a lower load for a longer duration of time.
I see. The high efficiency in the partial load is for high efficiency. The basic method is sliding pressure operation. And to keep and maintain the temperature even in the very low load. So that's the way to keep the efficiency very high even in the partial load. And that's my answer. Is that okay? Okay.
I think it is okay, and what you said is only two measures you are taking is sliding pressure operation. You are reducing pressure to the minimum possible values and trying to maintain main steam temperature and HRS temperature rated value even at the low pressure. Am I right?
Yeah, exactly. Can you hear me?
Yes.
Exactly. The sliding pressure is better way to keep the efficiency in lower load. Yeah, that's the major way to keep the efficiency high.
Sir, what are your suggestions on auxiliary power at low load? How to?
Oh, I see. I think it's tough question. For auxiliary power, we need to reduce the operating number of pumps or reduce the number of pulverizer. Reduce the number of pumps and pulverizer to the minimum. At least 2 meals operation is possible. So that's the way to reduce the auxiliary power in the partial load.
Okay, thank you. The next question is, what are the costs involved in CO2 utilization? This question is, I think, for the second presenter. I'll repeat the question. What are the costs involved in CO2 utilization?
Yeah, this question is for Mr. T. Wakayama. Mr. Wakayama, please.
Yes. What the cost of the CO2 utilization is right?
I'll repeat the question. What are the costs involved in CO2 utilization? I think he might be talking about CO2 capture and storage or something.
Yes.
About.
Yes, sir. Okay, can you hear me?
Yes, sir, we can hear you.
Yes. So the cost of the CO2 utilization it depends on the cost of the CO2 capture and storage and the transportation and something. So if the technology for the CO2 utilization for the methane and for the methanol or some other materials, it's a so we have a lot of the estimation, but it's a quite different the case by case. So basically, CO2 utilization based on the CO2 capture cost. Is right? Is it a full answer?
Okay, sir. Thank you. May we request all the audience to kindly write the question in the chat window. It's a very good opportunity to get some answers to some of our doubts. So kindly write the question. One question is, what is the experience in Japan on connecting the solar power grid with the thermal power plants? What are the problems you have faced and how you have overcome those problems?
I think this question is for me.
Yes, sir. Yes, sir.
And the question is introducing solar power to the thermal power units. Is that right?
The grid integration between renewable power and thermal power plants. What are the challenges you have faced and how you have overcome it?
What are the
grid integration?
Yeah, grid integration.
Yeah. Between the solar power and the thermal power plants. Because the solar power is available only in the daytime, how you are managing, what is your thoughts, how Japan has managed these kind of situations?
Yeah. Okay. In Japan, we have very huge amount of pumped hydro, and the capacity of pumped hydro is 20 gigawatt in Japan. And first, if the PV power is introduced and the PV generates in the daytime, the energy is stored to the pumped hydro first. And then at the same time, the thermal power plants stop their operation from the natural gas power and GTCC, followed by coal-fired power plant. And coal is very cheap fuel in Japan. So finally, the coal power plant is going to decrease the load ratio to minimum mode. And we need the frequency control by thermal power plants. So the coal power plant is operated at the almost minimum load and changing their the power generation power, always changing their power to control the frequency of the system. So coal power plant is going to be operated at minimum load. So that's the way to for the integration of the PV power in the power grid.
Okay, thank you. So, Chairman, with this we close our all questions. So you may continue. Thank you.
Thank you very much. 和歌山様、フォローありがとうございました。
こちらこそありがとうございました。
失礼します。
Okay. Mehul, I think we won't be able to listen from Mr. Kamachi Razaval.
Yeah, we are unable to hear him.
Okay. In fact, we were very keen to listen from Mr. Razaval because of the subject environmental management for thermal power plants, which is of immediate concern. We are going in a big way for integration of environmental equipment in Indian power stations. So we wanted to know the experience of Japanese utilities. Anyway, can I ask him to share his presentation so that the same can be shared with the delegates? Mehul. We have two very good presentations on this. The first one was on the research and development in CO2 utilization technology by Dr. Wakayama. This is a very important part of our decarbonization effort, that is use of larger scale use of CO2 for the production of methane. Though it is still under the R&D stage, and we are expecting some kind of commercial scale plant in 2030. We also came to know that this economics of methanation, that is the cost of electricity and cost of production of the hydrogen, is going to be of key concern. So we would be keenly watching this particular technology of larger scale utilization of CO2, and this will be an important step towards decarbonization. The second presentation was on this contribution of coal-fired power plants flexibility to a power systems, and we could see that this advanced coal-fired power plants is contributing in a big way for the flexibility in Japanese utilities. We could also come to know about this load frequency control performance, the available output range, the AGC30 model. These are all important concepts, and we think that we are also going in a big way, particularly as he said that, okay, they are going as low as 15% to 20% the technical minimum load. We are operating somewhere between 50 to 55%. So we have a long way to go for this technical minimum load. So with these remarks, I think this was a very good session, and where we talked about this larger scale CO2 utilization and this contribution of coal-fired power plants on the flexibility. With that, Mehul, I think I need to close this session.
Yes, sir.
I take this opportunity to thank everybody, all the speakers, all the delegates, all the organization for giving me this opportunity. Thank you once again. Thank you all.
Thank you. Thank you very much.
Yeah.
Thank you, everyone.
Yeah, the next session is at 2:30. We'll break for lunch now. Please join by 2:30.